so 10.1, I'm basically going to do week 10 and then I'll go back and do week 9 and week 8 in video form as well. So for the first bit of this, we've been talking about proof. So I'm just going to write a boring definition down for you guys to copy. Right, so mathematical proof is a logical and structured argument to show a mathematical statement, otherwise known as a conjective, is always true. So logical and structured to show something is true. You start with known facts, which we call theorems, and then you work through them logically, and then the final step in proof is the statement of what you've proven. So, to summarise, start with known facts. Take some logical steps. Prove something, and then state how you've proved it. So if you're trying to prove something, start with what you know for sure, do some stuff to it logically, and then say what you've proved by doing that stuff. And you need to show those steps for every kind of proof. So you have to do proof this year and next year. The proof in year 1 is called proof by deduction. So, for example, the product of two odds is always odd. So we have to somehow prove that the product of two odd numbers is always going to be odd. Now, to do this with logical steps, so proof and known facts, we're going to have to come up with an odd number. So we can say an odd number could be described as 2 times k plus 1. The reason we can do that is we can say 2 times any number is going to be even, and an even number plus 1 is obviously an odd number. So 2 times anything is even, even plus 1 is odd. So that's an odd number. So we can say the product of two odds, well there's one odd, 2k plus 1. Let's have another odd, 2p plus 1. And we'll expand these brackets and see if our result is always odd. So we get 4kp plus 2p plus 2k plus 1. Okay, so looking through this, we've got a load of even stuff. So if we take out a factor of 2, we can say it's 2 lots of 2kp plus p plus k plus 1. So 2 times something plus 1. 2 times anything is going to make anything even, like we said here. And then plus 1 is odd. So that is odd. So we can say, therefore, the product of two odds is always odd. And there's my proof. So that's an example of proof by deduction. Now there's a few of these you could be asked to do. I'll go for a couple more of these. again, just to summarise, state your theorems, assumptions and known facts first, show every step clearly from then on, make sure each step follows logically, cover all the possible cases. So here we had to prove it's true for all odd numbers, so we chose a general way of stating an odd number, and we wrote our statement of proof, therefore the product of two odds is always odd. Cool. If you're trying to prove results, like you might have seen in some of the assignments, so for example, if you're trying to prove is equal to a squared minus b squared, so difference two squares there. To do a proof like that, you need to start with one side only. So I mean only focus on either the left hand side or the right hand side. I usually recommend just start with the left hand side and work your way through until this equals what you started with on the right hand side. Don't mix them up or you get into a mess. Manipulate until it makes the right hand side. So do start with the left until it equals the right and include all your steps. Cool, alright, so that is proof by deduction and proving results. There's one more kind of proof that we have to do, which is proof by exhaustion. So proof by exhaustion is another method of proof, and it involves breaking the statement down into smaller cases and then proving each case separately. And it's best when there's only a small number of cases. If you had a lot of different cases, it's going to take a long time. So let's try an example of that. So prove all the square numbers are multiples of 4 or one more than a multiple of 4. Now that statement has two cases. It has odds and evens. So we're going to go through the two cases, prove each one separately, thus proving the overall statement. So for an odd number, we already said how you could kind of show an odd. So an odd would be 2n plus 1. And we've got to square this. So we're trying to prove that this is going to be multiple of 4 or one more than multiple of 4. So if we square this odd number, we're going to get 4n squared plus 4n plus 1. And we could factorise the 4 out to get 4n squared plus n plus 1. 4 times a number obviously is going to be a factor of or multiple of 4, and then plus 1 is one more than multiple of 4. So multiple of 4 plus 1. Even numbers, we could have 2 times any number, that's even, so an even number square, expand that, we get 4n squared, which is a multiple of 4. So therefore, all square numbers are multiples of 4 or more. So proof by exhaustion, proved it for odds, proved it for evens, and then statement of proof at Cool, right, there's one more kind of proof that we look at this year, which is proof by counterexample. So proof by counterexample is the last type. Basically, we can disprove something by finding one example that shows a statement is not true for all cases. So we're trying to disprove the sum of two consecutive primes is always even. So we need to think of two consecutive primes and then see if the sum of them is odd. So let's think of the easiest two primes, so 2 and 3. The sum of those, 2 plus 3 equals 5. 5 is not even, therefore statement is not true. Cool, right, let's try a couple of examples just based on different types of proof. So these can be counterexample, exhaustion, or deduction. Okay, if you want to pause it and have a go, you can. I'll start going through these now. So prove for all positive x and y that this is true. So we've got two fractions added together saying that they should be greater than or equal to 2. So adding two fractions, find a common denominator. So it's going to be x. So our common denominator will be xy. To get xy as our denominator here, we need to times the top and the bottom by x. So we'll get x squared over xy. And to get xy on the bottom here, we need to times this fraction on the top and the bottom by y. So we get y squared there. So we get x squared plus y squared over xy. So that should be greater than or equal to 2. And if we times both sides by xy, we get x squared plus y squared is greater than or equal to 2xy. And we can now take all that onto one side and say x squared plus y squared minus 2xy should be greater than or equal to 0. Now, we could rearrange this. X squared minus 2xy plus y squared greater than or equal to 0. And some of you will hopefully be able to spot that that's a expanded quadratic. So if you have x plus y all squared, it does expand to give you that. So you have to prove that that is greater than or equal to 0. Any number squared is greater than or equal to 0. So it is true. Right, second one. Use the counterexample to show that that's not true when x and y are not both positive. So, if we go for again an easy example, let's have x is minus 1, y is 2. If we put these into the equation, minus 1 over 2 plus 2 over minus 1 should be greater than or equal to 2. Here we've got minus a half plus or minus 2 greater than or equal to 2. Well, minus 2.5 is actually less than 2. So, not true when x is. So counters, I'm literally thinking of any example you can, and for a proper proof, work through well-defined steps, show everything on the way. Cool, that's it. So I'll do a separate video with a few questions. Maybe I won't.